Chapter 10, the Multiprocessor Scheduling Advanced. This chapter will introduce the basics of multiprocess scheduling, as this topic is relatively advanced and it may be the best to cover it after you have studied the topic of concurrency in detail. That is the second major easy piece of the book. After the years' existence only in the high end of the computing spectrum, multiprocessor systems are increasingly commonplace and have found their way into desktop machines, and laptops, and even mobile devices. The rise of a multi-core processor in which multiple CPU cores are packed onto a single chip at the source of the proliferation of the chips becomes popular as computer architecture had a difficult time making a single CPU much faster without using way too much power, and thus we'll all now have the few CPU available to us, which is a good thing, right? Of course, there are many difficulties to have the right that there arrival of time than a single CPU as a primary. One is more a typical application that some CPU and you wrote only use a single CPU. Adding more CPUs does not make the single application run faster. To limit these problems, you will have to write your usual application to run in parallel, perhaps using thread as discussed in great detail in the second piece of this book. Multi-threaded applications can spread work across the multiple CPU and thus run faster when given more CPU resources. Aside, advanced chapters. Advanced chapters requires materials from a broad swath of the book to truly understand, while logically fitting into a section that is earlier than a set of pre-required material. For example, this chapter on multiprocessor scheduling makes much more sense if you first read the middle piece of the concurrency. However, it largely fits into part of the book of visualization generally and CPU scheduling specifically. Thus, the recommended that such chapters be covered out of order, in this case after the second piece of the book. Figure 10.1 Single CPU with cache. Beyond the applications, the new problem that arises for operating system is not surprisingly that of the multiprocessor scheduling. Thus far, we've discussed the number of principles behind a single processor scheduling. How can it be extended those ideas to work on multiple CPUs? So what new problems must we overcome, and thus our problem. Crux: how to schedule jobs on multiple CPUs. How should the OS schedule jobs on multiple CPUs? What new problems arise? Do the same as old techniques work, or are new ideas required? 10.1 Background Multiprocessor Architecture. To understand the new issues surrounding multiprocessor scheduling, we have to understand the new and fundamental difference between single CPU hardware and multi-CPU hardware. This difference centers around the use of the hardware caches. For example, figure 10.1, and exactly how data is shared across multiprocessors. We discuss this issue further at a higher level. Details are available elsewhere, and particularly in our upper level of our perhaps the graduating computer architecture course. In the system of a single CPU, there are a hierarchy of the hardware caches that generally helps the processor run a program faster. Caches are small, fast memories that in general hold copies of popular data that are found in the main memory of the system. The memory, in contrast, holds all of data, but the access to the large memory is slower. By keeping the frequent access data in a cache, the system can make the larger and slow memory appear to be a fast one. Figure 10.2 Two CPUs with caches sharing memory. CPU memory. As an example, consider a program that issues a explicit load instruction to fetch a value from a memory, and a simple system with only a single CPU, and the CPU has a small cache, 64 kilobytes, a large main memory, Oh, and large main memory. And the first time the program issued this load, the data resided in the main memory and thus taken a long time to fetch, perhaps in the tens of the nanoseconds or even hundred. The processor, anticipating the data be the reuse, puts a copy of the loaded data into CPU cache. If the program later fetches in the system data into data item again, and the CPU first check for it in the cache. If it finds in there, the data is fetched much more quickly, say a few nanoseconds, and thus the program runs faster. Caches are thus based on the notion of locality, of which are two kinds, temporal locality, spatial locality. The idea behind the temporal locality is what a piece of data is accessed is likely to be accessed again in the near future, and is variable of the even instructions themselves being accessed over and over again in a loop. The idea behind the spatial locality that processes the data item address X is likely to access data simultaneously X as well. Here think of the program streaming through an array and instruction being executed at one after the other. Because the locality of these types exists in the memory program, hardware systems can make good guesses about which data to put in a cache and thus work well. Now the full trick part. What happens when you have a multiple processor in a single system with a single shared main program, as we figured 10.2? As it turns out, caching with multiple CPU is much more complicated. Imagine, for example, that a program running on a CPU1 reads data item with the data value D at address A. Because the data is not in the cache on a CPU1, the system fetches it from a main memory and gets it the value D, and the program then modified the value at address A, just update each caching with a new value D, writing the data through all the way to maintain its flow. So the system will usually do that later. Then they assume the OS decided to stop running the program, move it to the CPU2. The program then releases the value at address A. There is no such data in CPU2 cache, and thus the system fetches the value from the main memory and gets the old value D instead of the correct value D. Oops! This general problem is called the problem of cache coherency. And then there is a vast research literature describing different substitutes involved with solving the problem. SHW11. The hence we will skip all of the nuance and make some major points to take a computer architecture class or three to learn more. The basic solution is provided by the hardware. By monitoring the memory access, hardware can ensure the basic writing happens and the view of the single shared memory is preserved. One way to do is the bus-based system, as described above, is to use an old technique known as bus snooping. Each cache pays attention memory updates by observing the bus and connect them to the main memory. When a CPU then sees update for the data items it holds in a cache, it holds notice of the changing and either validates each copy that is removed from its own cache, or updated if it put the new value into cache 2. Write-back schemes, as hinted at above, make this more complicated because the write to the main memory isn't visible until later. So, but you can imagine how the basic scheme might work. 10.2, don't forget the synchronization. Given the cache, do all of this work to provide coherence. The coherency. Do programs or the OS itself have to worry about anything when they access the shared data? The answer, unfortunately, is yes. And is documented in great detail in the second piece of this book on the topic of the concurrency. While we won't get into the details here, we will sketch the review some of the basic ideas here. Assuming you are familiar with the concurrency, when assessing and in particular updating shared data items or the structure across the CPUs, mutual exclusion primitives as such locks should likely be used to guarantee correctness. The other approaches, such as building lock-free data structure, are complex and used to occasion. See the chapter on the deadlock and the peaks of the concurrency for details. For example, assume that we have a shared queue being accessed to multiple CPUs concurrently. Without locks, adding an or moving the element from CPU concurrently without locks, from the queue concurrently will not work as expected. Even with the underlying coherent protocol, one needs locks to automatically update the data structure to each new state. To make each more concrete, imagine this call sequence, which is used to remove an element from a shared linked list as shown in the figure 10.3. Imagine if threads on two CPUs enter this routine at the same time. If the thread 1 executes the first time, it will have the current value of the header store and in its TMP variable. If the thread 2 then executes the first line as well, it also have the same value of the header stores in their own private tempo variable. TMP is allocated in the stack, and thus each thread will have its own private storage for it. Thus, instead of each thread removing an element from a header of its list, each thread will try to remove the same header element, leading to all sorts of the problems, such as an attempted double free of the header element at line 10, as well as a potential returning the same data value twice. The solution of course, is making such routines correct via locking. In this case, locating a simple mutex, for example, pthread mutex tm, then adding a lock tm at the beginning of the routine and unlock at the end will solve the problem, ensuring that the code will execute as desired. Unfortunately, as we will see, such approaches is not without problems, and particularly whether regarding to the performance, specifically as the number of the CPU grows, access to a synchronized shared data structure becomes quite slow. 10.3 One final issue, cache affinity. One final issue arises in building a multiprocessor cache scheduler known as cache affinity. This notion is simple. A process, when run on a particular CPU, builds a fair bit of state in the cache and the TRS of the CPU. The next time the process runs, it often advantageous to run it on the same CPU, as it will learn faster if some of the state is already present in the caches on the CPU. If instead of the one runs a process in a different CPU, each time the performance of the process will be worse, as it will have to reload the state each time it runs. Note it will run correctly in a different CPU thanks to the cache coherence protocol of the hardware. Thus, the multiprocessor scheduler should consider cache affinity when making its scheduling decision, perhaps preferring to keep the process on the same CPU if at all possible. 10.4 Single queue scheduling. With the background in place, we now discuss how to build a scheduler for a multiprocessor system. The most basic approach is to simply use the basic framework for a single process scheduling by putting all jobs that need to be scheduled into a single queue. We call this scheduling queue multiprocessor scheduling, or SQMS for short. This approach has the advantage of simplicity. It doesn't require much work to take an existing policy that picks the best job to run on next and adapt its work on more than a CPU, where it might pick the best two jobs to run if there are two CPUs, for example. However, SQMS has obvious shortcomings. The first problem is lack of scalability. To ensure the schedule works correctly on multiple CPUs, the developers will have inserted some forms of locking into code, as described above. Locks assure that when SQMS code access to the single queue, say no to find the next job to run, the proper outcomes arise. Locks, unfortunately, can greatly reduce performance. particularly as the number of CPUs in the system grows. As contention for such a single log increases, the system spends more and more time in log overhead and less time to doing work the system should be doing. Note that it would be great to include a real measurement of this here and someday. The second main problem with SQMS is cache affinity. For example, let us assume we have 5 jobs to run, A, B, and C, D, E, and 4 processes our scheduling queue that looks like that. And then Q, A, and B, and C, then and learn. Over time, the assuming that each job is run on 4 time slice, then the another job is chosen. Here is a possible job scheduler across the CPUs. Because each CPU simply picks the next job to run from the globally shared queue, each job ends up with the balance bouncing around from CPU to CPU, thus doing exactly the opposite of what would make sense from the standpoint of the cache affinity. To handle this problem, most SQMS schedulers will include some kind of affinity mechanism to try to make it more likely that a process will continue to run the same CPU if possible. Specifically, one might provide affinity for some jobs, but move others around to balance load. For example, imagine the same 5 jobs schedules as follows. In this agreement, jobs A and B are data moved from across the processors, only job E migrating from CPU to CPU, thus preserving the affinity for most. You could then decide migrating different jobs the next time through, thus achieving some kind of affinity fairness as well. Implementing such a scheme, however, can be complex. Thus, we can see that QMS approach has its strength and weakness. Is straightforward to implementing a given existing single CPU scheduler, which is a definition has only a single queue. However, it does not scale well due to the synchronization overhead, and it does not readily preserve the cache affinity. 10.5 multi-queue scheduling. Because of the problem caused of the single queue schedulers, some systems opt for multiple queues. For example, one per CPU. We call this approach multiprocessor scheduling, or MQMS. In MQMS, our basic scheduling framework consists of multiple scheduling queues. Each queue will likely follow a particular scheduling discipline, such as the round robin. Thought of the course in any algorithm can be used. When a job enters the system, it is placed on exactly one scheduling queue according to some heuristic, for example random, or picking one of these fewer jobs than others. Then it is scheduled especially independently, thus avoiding the problems of information sharing and synchronization found in a single queue approach. For example, assuming that we have the system where there are just 2 CPU labeled CPU0 and CPU1 and some number of jobs enter the system, A, B, C, and D for example. Given that each CPU has a scheduling queue, now the UOS has to decide on which queue to place each job. It might do something like this. Depending on the queue scheduling policy, each CPU now has 2 jobs to choose from when deciding when it should run. For example, this round robin, the system might produce a scheduler that looks like this. MQMS has distinct advantage over SQMS, and that should be inherently more scalable as the number of CPUs grows, so too does the number of queues, and thus log and cache contention should not become the central problem. In addition, the MQMS intrinsically provide a cache affinity. Jobs stay on the same CPU and thus reap the advantage of reusing the cache's contents shared therein. But you've been paying attention, you might see that we have a new problem, which is fundamentally in the multi-queue based approach, load imbalance. Let's assume that we have the same setup as above, 4 jobs, 2 CPUs, but one of the jobs, say C, finishes. We now have the following scheduling the queues. If we run our round-robin policy on which queues of the system, we will see the result in the schedule. As you can see from the diagram, A gets twice as much CPU as B and D, and A and D, and which is not the desired outcome. Even worse, let's imagine that both A and B and finishing and the leaving just drops B and D in the system, and the two scheduling queues and a resulting timeline will look like this. How terrible CPU 0 is either. Insert dramatic and sinister music here. And thus our CPU usage timeline looks quite sad. So what should a poor multi-queue, a multiprocessor scheduler do? How can we overcome the insidious problems of the load imbalancing and defeat the available forces of the Decepticons? How do we stop asking questions that are hardly relevant to this otherwise wonderful book? Crux is how to deal with a load imbalance. How we should a multiple queues process scheduler handle the load imbalance so as to better achieve its desired scheduling goals. The obvious answer to this query is move jobs around, a technique which we once again refer to as migration. By migrating jobs from CPU to another, true load balance can be achieved. Let's look at a couple of examples to add some clarity. Once again, we have a situation where one CPU is idle and the other has some jobs. In this case, the desired migration is easy to understand. The OS should simply move one of the B or D to CPU 0. The result of this single job migration is evenly imbalanced load and everyone is happy. A more tricky case arises in our earlier example where A was left alone on CPU 0 and B and D were alternating CPU 1. And in this case, a single migration does not solve the problem. What would you do in the case? The answer, error, is the continuous migration of one or more jobs. One possible solution is keep switching jobs as you will see in the following timeline. And the figure first A is alone on CPU 0 and B and D alternate on CPU 1. After a few time slices, B is moved to compete with A on CPU 0 and while D enjoy the few time slices around the CPU 1 and thus load is imbalanced. Loaded and balanced. Of course, many other possible migration patterns exist, but now for the tricky part, how should the system decide to enact such a migration? One approach is to use the technique as a working stealing. With a working stealing approach, a source queue that is low on jobs will occasionally pick another target queue to see how full it is. The target queue is notably more full than the source code. Source will steal one or more jobs from the target to help balance load. Of course, there is a natural tension in such approach. If you look at the other queues too often, you will all suffer from high overhead, have troubling scaling, which was the entire purpose of implementing the multiple queue scheduling in the first place. If, on the other hand, you don't look at the other queues very often, you are in danger in suffering from severe load imbalances. Finding the right threshold remains, as is common in the system policy design, a black art. A Linux a Linux Micro 10.6 Linux Multiprocessor Scheduler. Interestingly, the Linux community, no common solution has emerged to building a multiprocessor scheduler. Over time, three different scheduler rules, the O1 scheduler, the completely fair share Fair Scheduler CFS and the BF Scheduler BFS and C. B. Hin the dissertation for excellent overview of the strength and weakness of the stat scheduler M11. Here we just summarize a few of the basics. Both O1 and CFS use multiple queues, where the VFS uses single queues, showing that both approaches can be successful. Of course, there are many other details which separate these schedulers. For example, the O1 scheduler is priority-based scheduler, similar to the MLF queues discussed before. Changing the best processes priority over time in the scheduler, though the highest priority in the order to meet the various scheduling objectives. The interactivity is a particular focus. CFS, in contrast, is deterministic proportional share approach, more like a stride scheduling as discussed earlier. BFS, the only single queue approach among the three, is also proportional share, but based on the more complicated scheme known as the earliest eligible virtual deadline first EEVFD. To read more about these modern algorithms on your own, you should be able to understand how they work now. Section 10.7 Summary. We haven't seen various approaches to multiple process scheduling. The single queue approaches SQMS is rather straightforward to build and balance load well, but inherently has differently with the scheduling to many processors cache affinity. The multiple queue approach MQMS schedules better than handles cache affinity well, but has trouble with low imbalance and is more complicated. Whichever approach you take, there is no simple answer. Building a general purpose scheduler remains a daunting task, as small code changes can lead to large behavioral difference. Only undertake such an exercise if you know exactly what you are doing, or at least getting paid a large amount of money to do so.